Good morning everyone. This tutorial is going to cover sheet 6. So let's start with question 2. A 50 ohm 100 MHz sinusoidal source is terminated in a 50 ohm load resistor. Determine the value of a capacitor that when placed across the output will reduce the voltage by 20 dB. So first let's start by drawing the equivalent circuit before adding the capacitor. So the question said we have a voltage source of a resistance 50 ohm is connected to a resistor load of 50 ohm. So if we add a capacitor to the load, what is the value of what will be the value of this capacitor that will reduce the voltage by 20 dB. So first we need to find a relation between this voltage and this voltage and to calculate the input impedance after adding the capacitor. So from the first circuit we are going to derive the V input dash, in which there is no capacitor here. So by using voltage division, Vn dash equal 50 over 50 plus 50 multiplying by the source voltage. So we get the input voltage dash equal to the voltage source over 2. While after adding a capacitor parallel to the load, we find that the input impedance from here is equivalent of this capacitor and this resistance are in parallel. So the input impedance is equal to RL, the resistance load, multiplying the impedance of this capacitor over the summation. So now we need to write the impedance of capacitor as a function of 1 over j omega c. Then we multiply by j omega c to remove this one and this one. So we get the value of input impedance is equal to 50 over 50 j omega c plus 1. Now since we need to define a relation between V input double dash and V input dash, in which the voltage decreased or the output voltage decreased by 20 dB after adding this capacitor, so we find that V input double dash by using voltage division from here. Now we get the equivalent resistance, which is equal in which these are two parallel. We combined it and we get the input impedance is equal to this value, and we have a resistance source is equal to 50 ohm. So now we need to define what is the V input double dash. By making a voltage division, we find that by substituting of the input impedance by this value 50 over 50 j omega c plus 1 over 50 over 50 j omega c plus 1 plus 50 the value of source resistance, and by doing some multiplication to simplify the final value, we found that V input double dash is equal to this value. So it is given that the capacitor, when it is placed parallel to the resistance load, it will reduce the voltage by 20 dB. Then it will reduce, so the value becomes negative 20. And we found a relation between V input double dash and V input dash from the two different circuits, V input dash from this circuit and V input double dash from this circuit after adding the capacitor. So now we need to find the value of this capacitor. So let's go back here by multiplying by 10 power negative 20 over 20. We removed the log Vn double dash, Vn dash. We substitute by the value we got from the above of this V input double dash and V input dash. And don't forget to substitute omega which is equal to pi f, and the frequency is given by 100 megahertz. So we finally arrive to this equation. Now I need you to focus how to get the value of this absolute value. Now if we draw the imaginary versus real, and I need to get the value of 2500 j omega c plus 100, the real value is 100, so on the x-axis I moved to a value 100, and then the imaginary part, which contains j, is equal to 500 omega c. Then the height will be 2500 omega c. So now I am standing on this point, which is equal to the 100 real part and the imaginary 2500 omega c. Now if I dropped a line from here, I will find it as a triangle. Now I need to find the value of 100 plus 2500 omega c in order to substitute it and get the value of the capacitance. So if we use Pythagoras theorem, we found that the absolute value of 100 plus 2500 j omega c, which is this value, square, is equal to the x-axis square plus y-axis square, which is equal to 100 square plus 2500 omega c, which is the height, square. So now if we need the value of 100 plus 2500 j omega c without the power, we just put a square root and get this value. So now I will replay or re-say what I have said. If we need to define or to get the value of a complex number, to get a real value of this capacitance, we draw a real part and imaginary part. The real part consists of a value of 100 ohm, so I put a point at 100. Then the imaginary part is equal to 2500 omega c, and this point declares this complex impedance. So if I need to get the value of this hypotenuse without a complex number, I just use Pythagoras theorem as follows: absolute of 100 plus 2500 j omega c square, now by using Pythagoras, is equal to x-axis square plus y-axis square. X-axis square is equal to 100 square plus the y-axis is equal to 2500 omega c square. By square rooting both sides, I get this value without the imaginary part. So just I drop it here, and then by powering both sides by 2 to remove the square root, I get the value of the capacitance, which is equal to 633.4 picofarad. That will make the drop voltage that if we placed it parallel to the load, it will drop the voltage by 20 dB. So let's move to the next question. Question number 3. An inductor is to be placed in series with a 50 ohm load to block a 100 MHz noise current. Determine a value for the inductance that will reduce the 100 MHz noise signal across the load by 20 dB. Again, so now we know we had two circuits. The first circuit is a simple circuit, just the noise voltage and inductor and resistors with 50 ohm, as mentioned here, at frequency 100 MHz. So this is the first circle. Again, we need to define a relation between V input dash and V input double dash if we placed an inductor in series with this resistor. So the first circuit, we are going to get the value of Vn dash, which is equal to I multiplied by this resistor. So obviously we are going to get the value of the voltage source or the noise voltage source. But for the second circuit, we added an inductor as mentioned in the question. So now to get the value of Vn double dash, we use a voltage division. So just this resistor 50 over 50 plus the value of L, which is equal to J omega L, multiplying the source voltage which is equal to Vn, we will get this equation. Since it is given when inductor is inserted in series with this circuit, the reduction of the noise voltage will decrease by 20 dB. Since there is a reduction, so we must put a negative sign here. So negative 20 equal 20 log 10, the ratio between Vn double dash over Vn dash, we will get this value is equal to 0.1 absolute over 50 plus J omega L. Again, if we need to define the value of 50 plus J omega L, which is a complex impedance, I need to convert it to a real impedance. I need to use this formula, which is I will draw a real part here and the imaginary part. The real part is equal to 50, so I went on the resistance on the real part axis to a point 50, then I moved up omega L. So now this point represents a complex impedance of 50 plus J omega L. To get the value of this hypotenuse, I just draw a triangle here by dropping this side. We get the value of the absolute 50 plus J omega L square, which is this hypotenuse. I get the value by squaring the x-axis, which is equal to 50, plus the y-axis, which is equal to omega L, all square. But if I need the value only without powering, I will just put a square root. So by plugging this value here, I can now get the value of the inductance, in which is if it's added in series to the circuit, the voltage will drop by 20 dB. So the value is equal to 0.8 microhenry. Now let's go back to our questions. Questions 1. 100 MHz noise signal is being applied to the input of a transistor amplifier whose input impedance is equal to 60 ohm at 100 MHz. Determine the value of capacitor that when placed across the input will divert 60% of this current. So let's declare it with a simple circuit like this. It is said that a transistor here and a capacitor is placed parallel to it, and the current passing through this capacitor will divert 60% of the input current. Now he need to define the value of this capacitor. In the question, it is given that the input impedance is equal to 60 ohm, and the value of In at frequency 100 MHz, find the value of this capacitance. So by using current division, I now need to define the current IC. So IC equal input impedance over input impedance plus the impedance of this capacitor, multiplying by the input current. By using a simple current division, we get to this value. IC will divert 60% of the input current as mentioned here. So now I can remove IC with 60% IN. IN will cancel with IN by using a sample multiplication and by using our what we have explained in the previous two questions. I can get the value of the capacitance that will divert the current here by 60% of the total current. So let's go back to our questions. For question 4, we have a graph here for a material called toroid of NIZN. The impedance is shown here, a relation between the impedance and the frequency, and it is required to determine the inductance, capacitance, resistance directly from the graph. So the value of resistance must be equal to this one. The value of inductance is when the slope is getting higher or increase, which is this line or this curve. And finally the capacitor is when it is degraded here. So obviously from the graph the value of the resistance is this one, so by going there it's approximately is equal to 1200. Since this value is 10 power 3, so it is 1000. So the value of resistance, question 4, directly from graph is equal to 1200. Now if we need to determine the inductance, the value of inductance is equal to 10 megahertz at frequency of this frequency is equal to, since this point is equal to 10 power 2, then it's 100. This point will equal to 200, 300, 400, 500. So at resistance or impedance 500 ohm, the value of this point is equal to 10 megahertz, which is equal to the frequency. So by using from the previous sheet or from the previous explanation, we find we can make the resistance is equal to omega L. So 500, which is the value of the resistance at frequency equal 10 megahertz. Now omega we can compensate it by 2 pi f, where the frequency is equal 10 megahertz. Now we get the value of the inductance, which will equal to 8 microhenry. Now for the value of capacitance, we at the same point here we found that the value of impedance is still equal to 500, and the value of frequency is equal to 200. So by equating the resistance and the capacitance impedance, and by substituting omega by 2 pi by 200, 10 power 6, 200 at this frequency, the resistance is equal to 500. Now we easily can get the value of the capacitance, in which is equal 1.6 picofarad. So let's go to next question, which is question 5. It's a simple question. Just remember or memorize the rule, and it will be a direct substitution. So let's go for this material toroid whose measured impedance is shown in figure 1. Estimate the relative permeability, which is mu r, of the material if there are 4 turns. Number of turns, the cross section area is equal to 0.5 multiply 0.5 centimeter, and the mean radius of the core is 1 centimeter. All you need to know is this formula. L is the mutual inductance, mu naught mu r n square number of turns, permeability. A is equal to the area, L mean is equal to pi r. So number of turns is given is equal to 4. Area is given by 0.5 multiply 0.5 centimeter. Don't forget to convert centimeter square to meter. So by direct substitution you can get the permeability of this material from this rule. Let's go to question 6. For the half-turn ferrite bed whose measured impedance is shown in figure 2, determine the equivalent inductance. So now from the graph we just need to spot the value of the resistance and then equating it with the inductance and get the value of L. So at frequency 1 megahertz, which is this point, we found the impedance is equal to 10 ohm. So by equating it 10 equal to omega L, since he need to determine the value of inductance. So 2 pi F is equal to 1 megahertz multiplying by L, in which you need to determine the value, equal 10 is the value of the resistance from the graph. Here 10 power 0 represents the frequency and 10 is the value of impedance. So we get the value of the inductor as he required. So let's go to question 7. Again, for the two half-turn ferrite bed whose measured impedance determines the capacitance. Now he needs to determine the capacitance. So at frequency 200 megahertz, at here the value is equal to 400. So here capacitance, as I said before, is the decaying or decreasing slope. So if you take this point, take this point, take this point, it's okay, but you need take the simple point here to get the value of the frequency, right? So I got this point, which is equal to 100 megahertz, equivalent to a resistance of 400 ohm. So by plugging it in this equation, now I can get the value of the capacitance. Now I need you to focus on the following questions, as it's very important, and I need you to focus from here. So let's start with question 8. An ideal common mode choke is constructed as shown in figure 4 here, with terminals A, B connected. If we connect A, B, the impedance seen looking into terminals A, B from here is equal to 300,000 angle 90 at 50 megahertz. So now for the first part, we have AB terminals are connected to each other. We get the value of input impedance is given as this value at frequency 50 megahertz. So let's continue with terminals, but with terminals A capital B small connected. A capital B small connected. If we connect these nodes together, A capital B node, the impedance with terminals at 50 megahertz seen looking into terminals A small b capital, A small b capital. If we look from here, the input impedance will be seen as this value. So what is required is determine the self and mutual inductance of the shock. So let's classify it into a simple parts first. So first, AB terminals are connected. Capital AB terminals are connected, and the impedance from here is given as 3000 angle 90 at frequency 50 MHz. So in the first equation, or in the first circuit, we found that AB now is connected, and the input impedance from here is given by this value at frequency 50 MHz. So let's assume the direction of current in this direction. So we moved by the current here, here, here. Now we find that the direction of the current is into the paper. The direction of the current is into the paper. So to determine the direction of the flux or magnetic field, we need to use right-hand rule, in which the direction of the thumb is the direction of the current, and the direction of the rest of the figures is the direction of magnetic field. So since this so the direction of this current is into the paper, the direction of the magnetic field will be to the right. So by continuing the direction of the current, we now need to determine the direction of the magnetic field here. Sorry. So now the direction of the current is out of the paper at this point. So by directing your thumb out of the paper, you will find the direction of the magnetic field is to the right. So now you can find that the direction of these two is opposite to each other. So by drawing an equivalent circuit to this circuit, we find that the terminals of AB capital is connected to each other. I draw this part as an inductor and this part as an inductor, and there is a mutual inductance between them. Each one had a self-inductance L. So by moving, since the current moving from this side, the first thing will be positive, other will be negative at V1. Then by continuing, the current will pass through this point, so it will be positive. And finally, we need to determine the value of V1 and V2 to get the input voltage, then get the value of L and M, which is the self-inductance and mutual inductance. So first equation, the current of V1, it will consist of J omega L I, L as there is an inductor here, and since there is a mutual inductance and both are in opposite direction, so I put a negative sign here. Negative J omega M I, M represent the mutual inductance. So at V1 this value is equal to J omega I multiplied by L minus M. So now if I need to determine the voltage 2 at this inductor, it will be the same. J omega L I is current, minus J omega I M is a mutual inductance. Again, the negative sign here, as they both are in opposite direction. Now if I need to determine the input voltage, it will be the summation of voltage 1 plus voltage 2 equal to this value, since it is given the input impedance has a value. So input impedance equal to input voltage over current. by plugging this equation here, now we can determine the value of input impedance is equal to J omega L minus M, where the value of input impedance is given as 3000 angle 90 equal to J by 2 pi omega. It is given at a frequency 50 megahertz, so 2 pi 50 megahertz L minus M. We got our first equation that relate between the self-inductance and mutual inductance. So since we have two unknown, now we need two equations to solve them. So as mentioned in the questions, the terminals A capital B is connected and A small b are connected. So A small B capital are connected and B small A capital are connected, and the impedance is given or seen from this is equal to 10 power 6 angle 90 by following the same procedures. Now the current is in this direction moving along the circuit, then it will go by this line. So as mentioned before, the direction of the current is out of the paper, so the direction of magnetic field is to the right. So continuing to the direction of the current through the wire, we found it passing through the node A capital, and then we find the direction of the current here is upward. So by using right hand rule, we find that the direction of the magnetic field is to the left. So now we found that phi 1 and phi 2 are moving along here in the same directions. That's why is the difference. The sign here is positive. So by drawing an equivalent circuit to this one, here is the inductor, the first one, here is the inductor of the second one, and along between them a mutual inductance, and they are moving on the same direction. So sign here is positive. So at V1 there is a L and M, so J omega L I plus J omega M I, and the value of second voltage will be the same, J omega L I plus J omega M I. L is a self-inductance, M is a mutual inductance. Now if we need to determine the input voltage of both, we just add them together. So input voltage will be equal to J omega I L plus M. I have the value of input impedance given as 10 power 6 angle 90. So if I need to determine L plus M, I just plug it here. I will cancel with I. All I will get is L plus M equal this value. Now I have two equations. I can solve them together and get the value of self-inductance and mutual inductance. This is the first equation, and this is the second equation here. So from 1 and 2, by solving them, we found that the self-inductance is equal 1.035 millihenry, and the mutual inductance is equal to this value. So finally, question 9. It is said an ideal common mode choke is connected between a source and load as shown in figure 5. Determine the amplitude of load voltage assuming all common mode current have been eliminated by common mode choke. So we have a source, we have a load, we have a common mode choke. The equivalent circuit is given here. The value of the L is equal to 30 microhenry and the value of M is equal to 27 microhenry. The voltage source is given as 10 sine omega t. Now all he needs is to determine the value of voltage here. You need to determine the direction of your phi by following the same procedures as we mentioned. So let's solve it. So this is equivalent circuit. We have two inductors with a value of 30 microhenry, and we have a mutual inductance between them is equal to 27 microhenry. All he needs to know is the value of VL, the load voltage at this resistor. So input impedance is equal to J omega L, which is this value, plus J omega L, which is this value, plus R and minus J omega M minus J omega M, again, as we have two inductors here, and by following the same procedures we found that the direction of this current or this we found that the direction of the flux will be opposite to each other. So we written here minus J omega M for the first one and minus J omega M for the second one. So we got the value of input impedance is equal to 1000 plus 3770 J, but I need the value of VL. So let's get the value of the input voltage, in which the current is equal input voltage over the input impedance. The input voltage is given by 10 sine omega t. Omega is equal to 2 pi f. The frequency is given 100 megahertz. So get the value equal to 10 over input impedance. I just got it here, 1000 plus this value. So I got the value of current passing through this circuit, which is equal to 2.6 milli, angle negative 75.14. All are complex. So now you need to determine the value of the load voltage across 1 kilo ohm. All you have to do is multiplying this resistor by the current passing through this circuit, which we got it from here. So now the voltage across this load will equal to I multiplied by 1000 equal to this value. So if you have any questions, please contact me or Dr. Hassan, and see you in the next tutorial. Thank you.